Welcome back. I have a wall here, and then on the left side of the wall, you have water here, and this wall holds the water back. And then I have the gate here, this AB section, that can rotate about point B. Right now, the gate is closed. The water that is held back by the structure exerts pressure on the gate AB. Now, the width of this gate is 8 meters. Due to the water pressure here, you have horizontal and vertical reaction forces in pin B and the vertical reaction force at point A due to the normal force. The density of water is 1000 kilograms per cube meter. And so your task is to find AY, BX, and BY. Good luck. Try it out on your own first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the reactions AY, BX, and BY. For that, we first need to know the fluid pressure that is exerted on the gate AB. The magnitude of that fluid pressure depends on the depth of water. Its pressure equals the density of water times G times the depth. In other words, it's 1000 times G times Z. And that's of course in pascals. However, since you know the width of this wall, which is 8 meters, you can represent this pressure distribution per unit length like this. Pressure times 8 meters. So that's gonna be 1000 times 8 times G times Z. That's 8000 times G times Z newtons per meter. So that's the magnitude of this pressure distribution. But the direction of it is normal to the surface of the gate. Let's get the total force that the gate experiences. We know that W at B, in this location here, it's 8000 times G times 5, because the depth is 5 meters. That's 40,000 G newtons over meter. And that's the same for this red arrow at point B and this yellow arrow at point B. They have the same length because the depth is the same. And then W at A equals 8000 times G times 9. That's 72,000 G newtons over meter. I have 9 here because I have 5 meters plus 4 meters. That's the depth of point A, 9 meters. You can find the length of this AB gate using Pythagoras' theorem like this. Length of AB equals 4 squared plus 3 squared, because you have 4 here and you have 3 meters here. And then I square root this sum and I will have 5 meters. And so to get the total force that this gate experiences, you essentially have to find the area of this yellow trapezoid. You could also integrate this thing, but in this case it's easier to simply find the area of this trapezoid. You will get the same area through integration, but with shapes like triangles and squares and trapezoids, you can find these areas directly. And that would be the total force on the gate. And this force will be WB plus WA over 2 multiplied by 5. It's going to be this one, which equals 280,000 G newtons. So that's the total force that this gate experiences due to water pressure. Essentially what you have here is the area of the trapezoid. Next, we have to find the center of pressure through which this force acts. you already know how to do it traditionally through integration. For example, you calculate the moment due to this distribution about point A, and then you divide that moment by this force, but there is an easier way. So let me draw this gate again, but horizontally. This is the trapezoidal pressure distribution, and now I can divide this distribution into two parts. I have the rectangular part and the right triangle part. The center of pressure of the rectangular part is in the middle of the gate, and that's due to symmetry. So 5 meters, that's the total length of the gate, and the rectangular part has the center of pressure 2.5 meters from point A and also from point B. But if you remember, then in this dam exercise, you also had a right triangle for your distribution. One side of the right triangle was 6 meters. It was this side that was also the side of the dam's wall that was receiving pressure from water. And then the center of pressure was 2 meters from the dam's bottom. So 1/3 of the dam's depth. That was your dV. The total length was 6 meters. Here you had 4 meters. And then dV was 2 meters. In other words, it was 1/3 of the entire length. That means that in our case, the center of pressure of this triangle, it's 1/3 of 5 meters from this corner here. So you would have 5 times 1/3, that would be 5/3 meters. And so the center of pressure of this right triangle is 5/3 meters from point A. And now you have to combine these two center of pressures, one from the rectangle and one from the right triangle. And this is how you do it. You calculate the total force for both sections, the rectangular and the triangular one. The total force due to the rectangular section is the area of this rectangle. You know that your WB, it's 40,000 G newtons over meter. So that's this one here. So you have 40,000 G times 5, which is the length of the gate, and that will be 200,000 G newtons. And then the total force due to the triangular section is the area of this triangle. Now if this point here, that's your WB, and this point here, that's your WA, then their difference is WA minus WB. So the force from the rectangular pressure distribution, that's going to be WA minus WB times 5 divided by 2. Now WA minus WB, that's 72,000 G minus 40,000 G, which is 32,000 G times 5 over 2. And that will give you 80,000 G newtons. And so if you add up these two forces, then you will have 280,000 G newtons, which is exactly what you have here. However, now we will get the moment about point A due to rectangular distribution, whose center of pressure was at 2.5 meters from point A. So for that, you have the moment due to this rectangular distribution about point A, and so I take the force due to this rectangular distribution, which is this one, and I multiply it by 2.5 meters. So essentially, instead of this rectangular distribution, I have this force here, and then I multiply it by this moment arm, 2.5 meters. And that will give me 500,000 G Newton meters. And then you do the same thing with the triangular pressure distribution. You calculate the moment about point A. So this is its center of pressure. Essentially, this one here is your force due to this triangular distribution. And 5/3 meters, that's your moment arm. So I have M triangle about point A. That's the force times 5/3 meters. And so that's the moment due to this triangular distribution about point A. And now, to get the center of pressure due to this general trapezoidal loading, you do it like this. You add up these both forces due to your triangular and rectangular distribution. That will of course give you your total force that you have here, and then you multiply that total force by this general CP that you have here, and right now it's your unknown, and then you add up both moments. That will of course give you the total moment about point A, and now this L bar CP, that's the sum of the moments over the sum of the forces. Now if you add up these two moments here, then you have this result, and then you would divide it by this total force, which is the sum of these two forces. It's this one here, and so you can cancel out the G's, and so you will have 95/42 meters, which is approximately 2.26 meters from point A. So this distance here, that's approximately 2.26 meters, and essentially this is the point through which this total force, this one, goes. Welcome back. And now that we have our center of pressure of the gate from point A due to this trapezoidal force distribution, we know that the force due to this distribution, which is this one here, F, it goes through this point, and of course it's perpendicular to the gate. And now what we need to do, we need to decompose this force. So let's say that I have an angle here, alpha, and we need to find this angle alpha in order to decompose this force into its rectangular coordinates. And so now, right here, I will have another angle, let's call it beta, and because of the fact that this force is perpendicular to the gate, due to geometry, this beta is also here, and you have a right triangle here as well. Now to find beta, that's easy. Beta equals inverse tangent of, and now you have 4 meters here, the opposite side, and 3 meters here, the adjacent side, so 4/3, and you also have this beta here, and you have 90 degrees here. That means that alpha equals 90 degrees minus beta. In other words, you have 90 degrees minus tangent inverse of 4/3, and that will give you approximately 36.87 degrees. And now you have 3 forces here, AY, BX, and BY. They hold this gate at rest. The gate does not translate, which means that in this case, the sum of all the forces in the x direction are 0 newtons, and also all the forces in the y direction are 0 newtons. And this gate does not rotate either. And that means that the sum of the moments is also 0. And it does not matter what point you take your moments about. To keep your gate from rotating, the sum of the moments about any point must be 0 newtons times meter. So you can just choose that point. I choose point B. Then I don't have to calculate moments for BX nor BY, because there is no moment arm. And so These are called the equilibrium equations, and we can use them to find these reaction forces. So let's first sum up all the forces in the x direction. To the right you have positive x, upwards you have positive y, so you have minus bx plus, and then this force here, due to this pressure distribution, times cosine alpha. That will give you a force in the x direction, and that must equal 0. Then you have ay plus by minus this force right here times sine alpha, and that will be 0. And now the sum of the moments about point B, it's going to be the following. You have minus ay times 3, that will be a clockwise moment due to this force ay, your 3 meters, that's your moment arm, till your point B, and then I'm going to take this total force, and then I multiply it by 5 minus 95 over 42 meters, and that must be 0. So remember this CP here, this number, it's measured from point A. The total length of the gate is 5 meters. So the distance from CP to point B, that's 5 minus 95 over 42 meters. And that will give you a counterclockwise moment. Note that for this moment, I did not have to decompose this force vector. That's because I had a moment arm from this force till this point B right away. You see that this distance along the gate, it's perpendicular to the force. And now I have 3 equations and 3 unknowns, bx, by, and ay, which you also have here. You know what your force is. It's this one here, 280,000 times g newtons. So I'm going to take this third equation, I'm going to rewrite it like this, and so instead of having 3 here, I'm going to put it down here. And so if you make the calculations, then you will have ay equals, and then you will have this result here. Then the first equation, it gives you bx equals F times cosine alpha. You know your force, F. Now alpha was approximately 36.87 degrees. And so if you put them all in this equation, you will have 224,000 g newtons. That's your bx. Finally, from the second equation, you have by equals F times sine alpha minus ay. You know your force, you know your alpha, you know your ay. If you make the calculations, you will have minus 87556 g newtons. It's negative, which means that your assumption about the direction of your by force was wrong. You assumed that by pointed up. However, it points down instead. And there you go. You have ay that points up, you have bx that points to the left, and you have by that actually points down, even though you initially assumed that it pointed up. Now we took the moments about point B, but feel free to experiment with it and take your moments about point A. You will have different equations, but in the end, your reaction forces will be the same. But I encourage you to convince yourself of that by going through the exercise yourself and find the reaction forces when you take your moments about point A. And there you go. Thank you very much. Welcome back. There is a mechanism here which is used to drain the area B when the tide water in area A goes down. In that case, the fluid pressure distribution from the B side is greater than from the A side, and the gate will swing open to the left, and then water flows from area B to area A, and then the level of water in B decreases. That's how you drain the B side. However, when the tide in area A rises, when you have more water on the A side, then the pressure distribution of the fluid from the A side is greater, and the gate will not swing open to the other side because it is stopped by this block at point D. And now consider this scenario. In area A, you have 3 meters of depth of water. In area B, you have 2 meters of depth of water. The density of water is 1000 kilograms per cube meters, and then the height of the gate is 4 meters. Then the width of the gate is 6 meters. So this is the height of the gate. It's this one here. You're seeing it from the side. But then as you go into the screen, the width of the gate is 6 meters. As a result, two reaction forces are produced, Cx and Dx. So you can see that the gate is not going to swing open because of this stop block. In the hinge C, you have Cx, and due to block at D, the gate experiences this force Dx. You cannot have vertical forces because the load distributions from both sides due to water are perpendicular to the gate, which means that they're horizontal. And so, what are Cx and Dx? Try it out by yourself first and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the reaction forces Cx and Dx. Now if this is again the gate, and here I have my water levels, and this is the A side and the B side, this is C, and this here is D, then on the A side, you have this pressure distribution. Let it be WA equals P times 6. 6 was the width of the gate, and P was the pressure in pascals. So you have WA equals 1000 times 6 times G times Z. Z was the depth. We assume that Z is positive as you go down. And of course it's in newtons over meter. So in total it's 6000 times G times Z. And now on the B side you have the same thing. WB equals 1000 times 6, which is the width of the gate, times G times Z. And that's 6000 times G times Z, newtons over meter. The total force from the A side is the following. First of all, WA at ZA equals 3 meters, and I should specify that this is ZA, and then here you have ZB, so two different variables, because you have different water levels here. And so WA at ZA equals 3 meters, that's 6000 times G times 3, which is 18,000 G newtons over meter. So the total force from the A side, that's 18,000 times G times 3 over 2. Essentially, I've computed the area of this triangle, and that gives you 27,000 G newtons. And as you have seen from the previous videos, when you have a distribution of a right triangle, then your center of pressure from the A side, it would be 1/3 of 3 meters from point D. So 1/3 of 3 meters, it would be 1 meter. And then the total force from the B side is the following. Now your total depth is 2 meters. So WB at ZB equals 2 meters. That's 6,000 times G times 2. That's 12,000 times G newtons over meter. And so just to clarify, this side here, that was this one, delta A maximum, and then this side here, it's this one, that's your delta B maximum. So the force from the B side, that's 12,000 G, which is this side, times 2, which is the depth of water on the B side, divided by 2. The 2's are cancelled, and so you will have 12,000 G newtons. Its center of pressure, which corresponds to the one on the B side, from point D, it's 1/3 of 2 meters. So it's 2 over 3 meters. And so now that we have our total forces on the A and B side due to our pressure distributions, and we have their respective centers of pressure, now we can calculate these two reaction forces, Cx and Dx. So I'm going to draw this gate again. This is C, this is D. Its total length is 4 meters. This is Dx, this is Cx. This is force A that acts through this center of pressure. The distance here is 1 meter. That means that the distance here must be 3 meters because the total length is 4 meters. Then here you have your FB and its corresponding center of pressure. This was 2 over 3 meters, which means that this one here, it's 4 minus 2 over 3. So let me have a common denominator here, 12. So I will have 4 times 12 here, minus 4 times 2 here. I have 48 minus 8 over 12, 40 over 12, which is 10 over 3 meters. So this distance here, that's 10 over 3 meters. So what I will do now, I will calculate the total moment, the net moment, about point C, and it has to equal 0 newtons times meter. So I have minus dx times 4 minus FB times 10 over 3, and then plus FA times 3. And that must be 0. You know your FB and your FA. So right away you can calculate your dx. So I'm going to have 4 times dx, 3 times FA, minus 10 over 3 times FB, and now all that I'm just going to divide by 4, and so I will get 10,250 G newtons. And then I'm going to sum up all the forces in the x direction. So I will have FA minus FB minus dx minus cx. That's 0. I know my dx, I know FB, FA, and so cx equals FA minus FB minus dx, and that's 4750 times G newtons. And there you go. You have your reaction forces. Your dx equals this one, and your cx equals this one. And now both results are positive, which means that your assumption about their directions were correct. Thank you very much.